Hello, everyone. How are you guys doing today? Good. Any question before we start? Any comments? Concern? You know, day by day, our class is getting smaller and smaller and smaller, even though nobody dropped. Just the attendance is getting lower and lower and lower. That's weird. I mean, it's not weird. Probably it's because I post all those videos, so they just don't want to come to the class. Even though attendance is 5% of the grade. Okay, so do you remember what we did in our last class? First, we talked about subspace. And when we talked about subspace, we talked about a few different types of subspace, like polynomial space, 2x2 matrix space, R2 space, R3 space. Do you remember all those things? A little bit. The last thing we did was a null space. What is null space? Who remembers? Null space. What is null space? Or at least null space contains what? Good job. The null space is the space which contains a solution for homogeneous system of equations. Okay, so basically when you try to solve a bunch of system of equations where the right side of the equal sign is all zeros, then after you solve them, whatever you get for your x, y, z or your variables, combining them in a vectored form, that's the null space. And do you know what is nullity? Do you remember? What the dimension of the null space? How do you find them? Alvin?
Then write out the equation. And for everything that's there, you put the value. Everything that's not there, you put a 0. And then you put it into the span.
Vectored form.
Yeah, vectored form.
So how do you determine the dimension of the space? Number of vectors. So after you solve your system of equations, depending on how many vectors you get as a solution, that's the dimension of your null space. So let's refresh your memory with one question. Definitely one of these will be in the exam. So our goal is to solve this. Can we use A inverse to solve this? Is it possible to use A inverse?
No.
Good job. Since it's not square, there is no way we can use inverse. That means our hope is reduced rational form. So we're happy with one, no problem. Our goal is to turn this 2 into 0. So we need to change row 2. How do we change row 2? The new row 2 will be the old row 2 and then minus what? 2 row 1. So if you do 2 row 1, it's 2, 2, 2, 0. And if you're subtracting them, they change the sign. So 2 minus 2 is 0. So we get the new row 1, 1, 1, 0. The new second row is negative 2 plus 2, 0, negative 2 plus 1, negative 1, negative 2 plus 0, negative 2, and then 1 minus 0, which is 0. So we are happy we have at least second element in the first column is 0. Next, maybe we can make this, no, never mind. Next, let's go for this one. Let's make this 0. If you want to make this 0, that means you have to change row 1. So what's the new row one? We want to make the second element in the first row 0. Shibu?
Plus row 2.
Plus row 2. So a new row 1 will be 1, 0, 1 plus 0 is 1, 1 minus 1 is 0, 1 minus negative 2 is negative 1, 0 minus 0 is 0. And then we have 0. We can divide this by negative 1 or multiply by negative 1. So we get 1, 2, 0. I forgot to ask you the question. How many variables we have here? 4 variables. This is x1, this is x2, this is x3, this is x4. And how can you tell? If the last row is not non-zero, that means last row is last row represent by a vector, not by a vector, by a variable.
Where did the 1, the bottom right?
Here, this one? Which one? 2101. This is given.
Second matrix. 1, 0.
So we have row 2 is 2101. And we are doing minus 2 row 1. So negative 2, negative 2, negative 2, 0. When you combine them, we get 0, negative 1, negative 2, 0. Not 0, sorry, 1. So we have 0, negative 1, negative 2, 0. Not 0. Oh, man. B. Thank you. It should be 1 because 1 minus 0 is 1. Okay, so we don't get a 0 here. We get a negative 1 here. So 1, 2, negative 1. And now we can, exactly, this is not 0 anymore. So if you add them, it becomes 1. 1 plus 0 is 1. Negative 1 minus 1 is 0. 1 minus 2 is negative 1. 0 plus 1 is 1. Yep. That means we can change one of these, either the first one or the second one. We can change this one. No, we cannot change this one. We can change the top one. Right? If you draw row 1, the new row 1 is row 1 plus row 2. No, that will change our 0 to 1. Never mind. We can use back substitution. Because if you try to change the x4 on the top row, then our x2 will not be 0 anymore. So we shouldn't change. So let's write out what information we have. x1 minus x3 plus x4 equals 0. Right? This is x1, this is x2, this is x3, and this is x4. So x1, 0, x2, and then negative 1, x3, positive x4 is 0. The second row is telling us we have x2 plus 2x3 minus x4 is 0. Right? Did I make a mistake anywhere? So let's write down the solution in a matrix format. Our x1 is, if you bring the x3 and x4 to the other side, we get positive x3, negative x4. And our x2 is negative 2x3 and positive x4. Right? We could at least solve for x1 and x2. That means x1 is 0x1, 0x2, 1x3, negative 1x4. Our x2 is 0x1, 0x2, negative 2x3, and positive 1x4. Then what is x3? x3 is what? x3 is x3, it's independent. x4 is also x4. So x3 and x4, they are free variable in this equation. So we write x3 is 0x1, 0x2, 1x3, 0x4. And our x4 is 0x1, 0x2, 0x3, and 1x4. So we have the coefficient invisible 1. So we write these ones down. So our null space is n of a. It's the span of the vector. This vector contains all zeros, so we're not going to take them. This column contains all zeros, so we're not going to take them. So these are useless. This one and this one, only these two, they have non-zero elements. So it's a span of 1, -2, 1, 0, the first vector. And then the second vector is 1, 1, 0, 1, the second one. So what is nullity? Means the dimension of the null space. 2, because we have two vectors. This is 1, and this is another one. 2. Any question? No question, no comments.
What's the difference between span and nullity?
Okay, so span means it covers, so the null space is covered by these two vectors. This is what span means. It covers by them. And nullity means how many vectors you have, how many independent vectors you have, which covers the entire space. We have 2 of them. So nullity is how many vectors you have, independent vector, how many independent vectors you have. And then that tells us the dimension of the dimension of your space. Now, you know 2 vectors. So the entire space is covered by the linear combination of these two vectors.
Span is the actual set.
Span means you are covering your space. So null of A is the span of these two, means the null space is covered by these 2 vectors. And then the linear combination of other vectors. Amaisha. The vectors given to you in the subspace or vector set, why do you define how many? No, we are given as a bunch of linear equations, and you're trying to solve them. So when you solve them, what do you get? We get the null space. What is null space? It's the solution set for your system of equations. Okay. And now we are going to watch some visualization of whatever we have. Okay, so let's have some fun with some videos. I love those videos because whatever I cannot tell you, explain to you for visualization, they actually tell everything with their good videos. So let's watch 2 of them. And then the rest of the lesson will be easier to understand. Any question before we start? No? So this one is talking about the span. What is span? What span mean? The linear combination. I just mentioned linear combination. What does that mean? And then we have with the span and linear combination, there's another word, basis, what they are. So it talks about that. And the next one will talk about more about something else.
In the last video, along with the ideas of vector addition and scalar multiplication, I described vector coordinates, where there's this back and forth between, for example, pairs of numbers and two-dimensional vectors. Now, I imagine the vector coordinates were already familiar to a lot of you, but there's another kind of interesting way to think about these coordinates, which is pretty central to linear algebra. When you have a pair of numbers that's meant to describe a vector, like 3, -2, I want you to think about each coordinate as a scalar, meaning think about how each one stretches or squishes vectors. In the xy coordinate system, there are two very special vectors. The one pointing to the right with length 1, commonly called I hat, or the unit vector in the x direction, and the one pointing straight up with length 1, commonly called j hat, or the unit vector in the y direction. Now, think of the x-coordinate of our vector as a scalar that scales I hat, stretching it by a factor of 3, and the y-coordinate as a scalar that scales j hat, flipping it and stretching it by a factor of 2. In this sense, the vector that these coordinates describe is the sum of two scaled vectors. That's a surprisingly important concept, this idea of adding together two scaled vectors. Those two vectors, I hat and j hat, have a special name, by the way. Together, they're called the basis of a coordinate system. What this means, basically, is that when you think about coordinates as scalars, the basis vectors are what those scalars actually, scale. There's also a more technical definition, but I'll get to that later. By framing our coordinate system in terms of these two special basis vectors, it raises a pretty interesting and subtle point. We could have chosen different basis vectors and gotten a completely reasonable new coordinate system. For example, take some vector pointing up and to the right, along with some other vector pointing down and to the right in some way. Take a moment to think about all the different vectors that you can get by choosing two scalars, using each one to scale one of the vectors, then adding together what you get. Which two-dimensional vectors can you reach by altering the choices of scalars? The answer is that you can reach every possible two-dimensional vector, and I think it's a good puzzle to contemplate why. A new pair of basis vectors like this still gives us a valid way to go back and forth between pairs of numbers and two-dimensional vectors, but the association is definitely different from the one that you get using the more standard basis of I hat and j hat. This is something I'll go into much more detail on later, describing the exact relationship between different coordinate systems. But for right now, I just want you to appreciate the fact that anytime we describe vectors numerically, it depends on an implicit choice of what basis vectors we're using. So anytime that you're scaling two vectors and adding them like this, it's called a linear combination of those two vectors. Where does this word linear come from? Why does this have anything to do with lines? Well, this isn't the etymology, but one way I like to think about it is that if you fix one of those scalars and let the other one change its value freely, the tip of the resulting vector draws a straight line. Now, if you let both scalars range freely and consider every possible vector that you can get, there are two things that can happen. For most pairs of vectors, you'll be able to reach every possible point in the plane. Every two-dimensional vector is within your grasp. However, in the unlucky case where your two original vectors happen to line up, the tip of the resulting vector is limited to just this single line passing through the origin. Actually, technically there's a third possibility too. Both your vectors could be 0, in which case you'd just be stuck at the origin. Here's some more terminology. The set of all possible vectors that you can reach with a linear combination of a given pair of vectors is called the span of those two vectors. So restating what we just saw in this lingo, the span of most pairs of 2D vectors is all vectors of 2D space, but when they line up, their span is all vectors whose tip sit on a certain line. Remember how I said that linear algebra revolves around vector addition and scalar multiplication? Well, the span of two vectors is basically a way of asking what are all the possible vectors you can reach using only these two fundamental operations, vector addition and scalar multiplication. This is a good time to talk about how people commonly think about vectors as points. It gets really crowded to think about a whole collection of vectors sitting on a line, and more crowded still to think about all two-dimensional vectors all at once, filling up the plane. So when dealing with collections of vectors like this, it's common to represent each one with just a point in space. The point at the tip of that vector, where, as usual, I want you thinking about that vector with its tail on the origin. That way, if you want to think about every possible vector whose tip sits on a certain line, just think about the line itself. Likewise, to think about all possible two-dimensional vectors all at once, conceptualize each one as the point where its tip sits. So in effect, what you'll be thinking about is the infinite flat sheet of two-dimensional space itself, leaving the arrows out of it. In general, if you're thinking about a vector on its own, think of it as an arrow. And if you're dealing with a collection of vectors, it's convenient to think of them all as points. So for our span example, the span of most pairs of vectors ends up being the entire infinite sheet of two-dimensional space. But if they line up, their span is just a line. The idea of span gets a lot more interesting if we start thinking about vectors in three-dimensional space. For example, if you take two vectors in 3D space that are not pointing in the same direction, what does it mean to take their span? Well, their span is the collection of all possible linear combinations of those two vectors, meaning all possible vectors you get by scaling each of the two of them in some way and then adding them together. You can kind of imagine turning two different knobs to change the two scalars defining the linear combination, adding the scaled vectors and following the tip of the resulting vector. That tip will trace out some kind of flat sheet cutting through the origin of three-dimensional space. This flat sheet is the span of the two vectors, or more precisely, the set of all possible vectors whose tips sit on that flat sheet is the span of your two vectors. Isn't that a beautiful mental image? So what happens if we add a third vector and consider the span of all three of those guys? A linear combination of three vectors is defined pretty much the same way as it is for two. You'll choose three different scalars, scale each of those vectors, and then add them all together. And again, the span of these vectors is the set of all possible linear combinations. Two different things could happen here. If your third vector happens to be sitting on the span of the first two, then the span doesn't change. You're sort of trapped on that same flat sheet. In other words, adding a scaled version of that third vector to the linear combination doesn't really give you access to any new vectors. But if you just randomly choose a third vector, it's almost certainly not sitting on the span of those first two. Then, since it's pointing in a separate direction, it unlocks access to every possible three-dimensional vector. One way I like to think about this is that as you scale that new third vector, it moves around that span sheet of the first two, sweeping it through all of space. Another way to think about it is that you're making full use of the three freely changing scalars that you have at your disposal to access the full 3 dimensions of space. Now, in the case where the third vector was already sitting on the span of the first two, or the case where two vectors happen to line up, we want some terminology to describe the fact that at least one of these vectors is redundant, not adding anything to our span. Whenever this happens, where you have multiple vectors and you could remove one without reducing the span, the relevant terminology is to say that they are linearly dependent. Another way of phrasing that would be to say that one of the vectors can be expressed as a linear combination of the others, since it's already in the span of the others. On the other hand, if each vector really does add another dimension to the span, they're said to be linearly independent. So with all of that terminology, and hopefully with some good mental images to go with it, let me leave you with a puzzle before we go. The technical definition of a basis of a space is a set of linearly independent vectors that span that space. Now, given how I described a basis earlier, and given your current understanding of the words span and linearly independent, think about why this definition would make sense. In the next video, I'll get into matrices and transforming space.
Today, we explore some of the basics of linear algebra. This includes understanding what it means for a set of vectors to be linear independent, to span, or to form a basis within a field. We consider the set of vectors v1 through to vm in a field Rn. This means column vectors with n entries. We first consider the linear combination of our vectors v1 through to vm. This means we have a constant before every vector before they're added together, i.e. x1 through to xm are all constants. Now, say this linear combination equaled the zero vector, and let's say this is only the case if all of our constants equal 0. Well, this is what it means for v1 through to vm to be linear independent in Rn. So let's look at an example. Say we have three vectors in R3 and we want to know if these are linearly independent. Well, let's say v1 equals 3, 2, 2, v2 equals 5, 3, 2, and v3 equals 4, 1, minus 5. So the question we're asking is, if we put this into a linear combination equaling the zero vector, is it necessarily the case that x1, x2 and x3 equal 0? Well, we can convert this linear combination into a matrix form, to which we can conduct Gaussian elimination to find out what these constants need to be. If you haven't already, I recommend watching my video on Gaussian elimination so you understand what's going on here. I'll link it in the description below. So returning back to our matrix, we want to convert this into reduced echelon form. We start by subtracting row 2 from row 1, then we subtract 2 times row 1 from row 2 and 2 times row 1 from row 3, then we times row 2 by minus 1, then finally adding 2 times row 2 to row 3 and timesing by minus 1. And there we have it, we've converted our matrix into reduced echelon form. So putting this back into the system of equations and equating our coefficients, we see that x3 has to equal 0, which implies that x2 equals 0, and finally x1 equals 0. So we have that these three vectors in R3 are linearly independent. Let's return back to looking at our general sequence of vectors v1 through vm in Rn. Let's now say that our linear combination of our vectors equals some arbitrary element b in Rn. If it's the case that there always exists an x1 through xm in the real numbers such that this statement holds, we say that v1 through vm span Rn. So now, how do we test this? Well, if we bring back our example before, but the reduced echelon form matrix, if it's the case that there's no rows full of zeros, we can say that it spans. But here, changing that one element means that this set of vectors would not span R3. Let's move on to the last definition of this video, looking at bases in Rn. So, if we have v1 through vm, we say it's a basis if v1 through vm spans Rn and v1 through vm are linearly independent in Rn. The most trivial basis of Rn is called the standard basis. Here, we have that the ith element of the ith vector equals 1 and the rest of the elements are 0. To conclude this video, let's contemplate the main theorem for Rn. This brings together all the topics we have covered thus far. The first part of this theorem is that every basis in Rn has n elements. So let's consider m vectors in Rn. Let's say that this forms a basis. So we put this into matrix form and convert it into reduced echelon form. To span Rn, it must have a leading entry in every column, and to be linearly independent in Rn, it must have a leading entry in each row. Therefore, we have that m must equal n, and that every basis must have n elements. We move on to the second part of this theorem, which follows from what we just said. We have that these following statements are all equivalent. For a set of vectors v1 through to vn in Rn, if these form a basis, then they also span Rn, and they are also linearly independent in Rn. Throughout this video, we've only contemplated results in the real numbers, but this also generalises into complex numbers and any other field. So I hope you've learned something new from this video or consolidated some old knowledge.
Okay, let me take the attendance first. Brendan C. absent. Joseph absent. Justine Absent. Gibran, absent. Shibu here. Michelle. Jack. Absent. Ashif here. Darius, absent. Winston. Abigail, absent. Shane. Emily. Kanar, absent. Christine, absent. Edison, here. Maisha, here. Brendan, here. Elvin, here. Shafal, absent. Alexander, here. Shitila, absent. Wenchuan, here. Kailun, here. Kailun, no fun, please. Okay, so I hope now you know what linear combination means, linear independence means, span means, basis mean. Right? You have some idea about this terminology? If you have some idea, then we can do some examples. So linear combinations mean you can multiply your vectors by some constant and then add them. Whatever you get, all this combination is a linear combination. Span is set of all linear combination of the vectors that span your entire space. Spanning set is the set the set V1 to Vn is a spanning set of V if and only if every vector in V can be written as a linear combination of all these vectors. Linear independent means they are not, you cannot write one of them in terms of other one. Okay, so for example, if you have three vectors, 1, 2, 3, 4, 8, 12, 8, 16, 24, you can clearly see they are not linearly independent, right? Because if you multiply 1, 2, 3 by 4, what do you get? The second one. And if you multiply this by 8, you get the third one. So these three vectors, they are not linearly independent. One vector can be rewritten in terms of other vectors. On the other hand, if you look at the second set of vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1, they are linearly independent. And they are linearly independent because there is no way we can multiply one vector or two vectors with some constant and you get the third vector. In general, if you have Rn space, you can have maximum n independent vector. So if you are in R2 space, then you can have maximum 2 linearly independent vector. If you have 3 vectors in R2, that means the third one must be a linear combination of the other two, or at least one of them. Same thing if you're in R3, you can have maximum 3 linearly independent vector. But if you have a set that has 4 vectors, one of the vectors is definitely a linear combination of the other vectors. Why do you care about linear independency? Because if you want to span a space, all the vectors must be linear. Can I flip my page? All the vectors must be linearly independent. If we have some vector that is not linearly independent and it's the dimension of the vector is same as in your space, then something is wrong. The set cannot be a spanning set. Means, for example, this doesn't span R3. Why not? Because even though we have 3 vectors, but they are not linearly independent. On the other hand, this spans R3. Why? Because we have 3 vectors in R3. So R3 can have maximum 3, and we have all 3. And what I was saying? They are linearly independent. So if you have 3 linearly independent vectors in R3, that means they span the entire space, entire R3 space. What is basis? Basically, it's the vectors that are linearly independent and they span the space. The key idea behind a basis is that it provides a unique and minimal representation of vectors in a vector space. Any vector in the vector space can be uniquely expressed as a linear combination of the basis vectors. And no additional vectors are needed to span the vector space. For example, in R2 space, we have two standard bases, 0, 1, 1, 0. So if you have 1, 0, 0, 1, that means you have a set, you have two bases. They are bases. Why? Because every other vector you can find by a linear combination of these two vectors, 1, 0, 0, 1. So R2 has two standard bases. The standard bases we represent them using the sign E1, the notation E. E1 for R2 is 1, 0. E2 for R2 is 0, 1. So basically this is the X value, this is the Y value in XY plane. Here's what it means. The standard basis for R3 means if you're in 3D space, then you have X, Y, Z. So we have three standard bases. This is the X value, this is the Y value, and this is the Z value. So 1, 0, 0 represent X, 0, 1, 0 represent Y, and 0, 0, 1 represent 3. Not 3, sorry. Z. So these are standard. Now without the standard, we have other bases also. For example, here, 1, 1, 1, 0, 1, 1, 2, 0, 1. These are three linearly independent vectors. So they also are three bases. They span the entire R3. Same thing this one, 1, 1, 1, 1, 1, 0, 1, 0, 1. They are linearly independent. They span entire R3, so they are bases. Okay. So basis for Rn must have exactly n vectors. For linearly independent, we can have maximum n linearly independent vector in Rn space. But for basis, it has to be exactly n vectors for Rn space. Means if you're in R2 space, you have to have exactly two bases. If you're in R3 space, you have to have exactly three bases. So bases are exact as your space numbers, space dimension. R2 needs 2, R3 needs 3, R4 needs 4. But for linearly independent, it could be less, but cannot be more. Now, when you do linear combination, what type of operations are allowed? These are some examples. If you have only V1 or only V2, we can say, well, that they are linear combination. Why? Because we can rewrite V1 as 1V1, 0V2, 0V3, like the way we did to find the null space. So it's a linear combination. Same thing if you do something like 3V1, FV2, 10V3, this is a valid linear combination. Why? Because 3, 1, half 10, all of these are constant real number, and you are adding all the constant multiples. Also, you can subtract the vectors. V1 minus V2 minus V3 is a valid one. So what is invalid? Something like this. If you try to multiply your vectors like V1 times V2, it's invalid operation. If you try to square a vector, it's an invalid operation. It cannot do that. And if you try to add a constant, it's an invalid operation. So you cannot add a constant, you cannot use a power, you cannot multiply them. The only valid ones is a constant multiplication and scalar addition. Sorry, scalar multiplication and addition, vector addition. So only two things, scalar multiplication and vector addition. Scalar addition is not permitted. Power, not permitted. Product, not permitted. Okay. Blah, 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 blah. All of these are given in the thing video. So, okay, so span of one vector. If you are in R2 space and you have only one vector, okay, only one basis, only one vector, then what do you have? Not basis, actually, one vector. If you have, then what do you get from all the linear combination? So let's say we have only one vector in R2 space. How do you know it's R2? Because you have two elements. Depending on how many rows you have, you identify which space you are in. If you have 2 rows, you are in R2. If you have 3 rows, you are in R3. If you have 4 rows, then you are in R4. So we are in R2 because we have 2 elements, 2 rows. Now let's say we have one vector, 1, 1. That means all the linear combination for this 1, 1 could be 2, 2, 3, 3, -1, -1, -2, 2, -3, 3, all those things. So basically, only constant multiplication is allowed, and whatever you get, that's a linear combination. The result is a linear combination of this vector. So what happens then? If you have the vector 1, 1, so x value is 1, y value is 1, and if you try to get all the linear combination of this 1, 1, the result is actually just a line. You cannot land anywhere outside of this line. It doesn't matter what number you multiply by, the result will always be on this line. So if you have only one vector in R2, the span is just a line. Okay, it means one vector can cover only a line in 2D space. It cannot cover the entire space. Only a line can be covered by that. But if you have 2 vectors, then the scenario is different. Now, depending on what type of vectors you have, if you have 2 dependent vectors, means one vector is a multiple of the other vector. So let's say you have one vector 1, 2, and the other vector is 3, 6. Obviously, we see that our V2 is 3 times V1. So this one is independent, but this is not independent. This one is a dependent vector. It depends on the first vector. So if you try to do a linear combination of these two, all the choices you have, they will have the same result. They will land on the same line. You cannot find a point that is lying outside of your plane, outside of your line. For example, here, 4, 8. So if you go x4 up 8, it will be somewhere on the line. If you get -1, -2, -1, -2, it will be somewhere on the line. And how do you get 4, 8, -1, -2? It's a linear combination of V1 and V2. For example, if we add them, V1 and V2, we get 3 plus 1, 4, 6 plus 2, 8. So the first one is the addition. The second one, if you subtract V1 minus V2, then 1 minus 3 is -1, 2 minus 6 is -4, sorry. This should be -4. I should change here. So all these linear combination, they can only land on a line.
Should be -2, right? Because 1 minus 3 is -2.
Oh, then the point is another linear combination. So you can do any type of linear combination. For example, how do you get the other one? Let me see. 1, 2, 3, so 2 times. 2 times V1 minus V3, V2. If you have V2 minus twice V1, what do you get? Twice V1 is 4, no, sorry, 2, 4. And you have 3, 6, 3, 6. So if you do the subtraction, 2 minus 3, oh, that's it, this is what I got. 2 minus 3 is 91, 4 minus 6 is 92. It's a linear combination. They don't have to be addition and subtraction. It's a linear combination. So it doesn't matter what type of linear combination you have, the end result will always be on the line. So what is this telling us? It's telling us that if you have 2 dependent variables, it's same as you have 1 independent variable. So the span is only a line. You cannot cover the entire plane. You can cover only a line. But there's a different story if you have 2 independent variables. If you have 2 independent variables and you take a linear combination of these 2, then you can cover the entire plane. For example, if you do 2, twice their sum, then it's this direction. If you do 3b plus w, it's a little bit tilted toward the x-axis. Negative b, negative w is a little bit downward. And then see, if you keep taking all the linear combination, all possible linear combination of these two vectors, you're going to cover the entire plane, entire xy plane. So what does that mean? If you have two linearly independent variables in R2 space, it covers the entire xy plane. And that covering is called span. So two linearly independent vectors that span entire xy plane or entire R2 space. This is what it means. So in the exam, I'm going to give you a multiple choice. Is this true or false? Two linearly independent vectors span entire R2. Two dependent vectors span entire R2. Is it true or false? Something like that. Okay. Any questions so far? No? We also noticed it says if the vectors are dependent, then removing one vector doesn't change anything, doesn't change your span. So if you have two dependent variables, it's same as you have only one independent variable. So the span is just a line. It doesn't matter if you have 2 or 3 or 4 dependent variables. The result is always the line. So if you have dependent variables, you can remove them however you want or whichever you want. The result will be same as the original independent variable. Like if you have one independent variable, it's same as if you have two dependent variables. It doesn't matter. On the other hand, if you have independent vectors, then you have a different story. Depending on which space you are in, if you're in R2 with two independent variables, I'm saying variable, two independent vectors, it spans the entire space. If you're in R3 with three independent vectors, then you are covering the entire space, R3 space. So it spans entire R3. Okay, but if you have 4 vectors in R3, the fourth one definitely has to be a linear combination of other vectors. So if you move one of them, it doesn't change your span. You get the same span as if you have 3 independent vectors. So if you have anything extra, it doesn't matter whether you have the extra or you remove them, it doesn't matter. Okay. Now, why you are doing all of this? The main thing to do, the main reason behind learning all of this is to figuring out if you have a set, does the set span some space? Or are they linearly independent? Or are they basis for the space? Okay, so figuring out all this information. So how do you figure out linear independency? Like how do you know whether two vectors are linearly independent or not? 2 is easy to figure out. You just have to check whether you can multiply one by some constant and get the other one. But if you have 3 vectors, how do you know they're linearly independent or not? Or if you have 4 vectors, how do you know? So if you have only 2, your life is easy. We just have to check if one vector is constant as another vector. If it is, then they are dependent. If they are not, then they're independent. And if you are in larger space than R2, like R3, R4, R5, then the easiest way to figure them out is that find the determinant. So create a matrix with all the vectors given to you and see what's the determinant of the vector, determinants of the matrix. If the determinant is not 0, then they are linearly independent. But if the determinant is 0, then they are linearly independent, not independent. Okay. So if Rn has m linearly independent vectors, then the set of vectors span Rn, and the set is the spanning set for Rn. So if you are in R2 with two linearly independent vectors, then the set is a spanning set. It spans entire R2. If you have 3 linearly independent vectors in R3 space, those vectors create, right? Those vectors creates a spanning set. It means they span the entire R3. A lot of information. But now let's have some fun. Determine whether these vectors are spanning set for R2. So in order to be a spanning set, a requirement is that they have to be linearly independent. So R21 and 32 linearly independent.
Yeah.
How do you know? Yes.
The other isn't a constant of the other.
So 2, 1, there is no way you can multiply 2, 1 by something and they will turn into 3, 2. It's not possible. So when you're in R2, your life is easy. So let's do both of them, both methods. The first method says, no, second method says is the determinant, so is the constant. So it's definitely no, because BECAUSE, because 1, 2, 1 multiplying by any constant C will never gonna give you the vector 3, 2. It's not possible. Or second method, another method is if you look at the determinant. So if you have the vector 2, 1, 3, 2 written in a matrix format, its determinant is 2 times 2, 4, minus 3 times 1, 4. Sorry, what I'm saying. 3 times 1, 3, and 4 minus 3 is 1. 1 is not 0. So if the determinant is not 0, they are good. They are independent. Okay, so which method is easier? You can use that method. Any question on this one? No? How about the next one? 2, 3, and 4, 6. Do they span at, what's the question? Whether the following is a spanning set for R2 means are they linearly independent?
They're not.
Why not?
What about 2?
So 2 times 2, 3 will give you 4, 6. So it's a linear combination. They're not independent.
When you say they are linear combination, you mean 2, 3, and 4, 6 are linear combination.
It means 2 and 2, 3, and 4, 6, they are linear combination of something. So if you multiply 2, 3 with 2, it's the other one. Here, basically, it means scalar multiple. One of them is scalar multiple of the other one. Okay. Now we have 3 vectors in R2. Are they linearly independent? Do you remember what did I tell you about linear independent? How the linear independence dependency is connected with your space dimension. In R2 space, how many maximum linearly independent vector you can have? 2. But how many is given to us? So one of them definitely is not independent. In R3, we can have maximum 2 linearly independent vectors. So one vector here is definitely, how to spell definitely? Define definitely. Is a linear combination of the others. But do you know at least how many independent vectors we have? Every vector has at least one independent vector. It's definitely. So here, how many independent vectors do we have? One or two?
Two dependent vectors.
So how many independents? One. So this space has only one independent vector. It's definitely the span. So it could be anything. It could be -1, 2, or it could be 1, -2, or it could be 2, -4. One of them is independent, and the other two depends on the independent one. So every space has at least one. So you can never say 0. It's always at least one. So the answer is no. So it says the system are not independent. There's only one independent.
Only one of them is independent.
Because every space has to have something, right? And then the others is a combination of that one thing, the scalar multiplication of that one thing. So which one is the original one? We don't care. But we do know that there is one original and everything else is a combination, a scalar multiple of that one vector. So it's definitely not a spanning set.
What happens if one of the vectors is a prime?
It doesn't matter. What do you mean prime number? 1, 3, they're prime.
Like it can't be multiplied by into the.
You can always multiply anything by a scalar. It's possible. So you have 1, 3. These are prime numbers. You can multiply them by any number. You can multiply them by 5, 10, 15, 2, 10, 2, 20. You can multiply them anything. So one vector is independent. And the other vector is a scalar multiple of that independent vector. And here we have one only, because if you pick the first one to be independent, then the second one is -1 times the first one. So if this is V1, then our V2 is -1 V1. Then our V3 is -2 V1, right? So there's only one independent. And if you only one, it doesn't span. It's just a line. It doesn't span the entire R2. In order to span the entire R2, you have to have two independent vectors, not one. Okay, now which space is it? Oh, I always decided. Let's say I didn't know that, okay? So which space is it? 3D or 2D? R2 or R3? 3, because you have 3 rows. 1, 2, 3. So if you don't see the space mentioned, you just have to count how many rows you have. If you have 3 rows, that means you're in R3 space. It doesn't matter how many vectors you have. It depends on how many rows you have. So what do you think? 1, 0, 0, 0, 1, 1, 1, 0, 1. This set of vectors, do they span entire R3? Now this one is hard to figure out the linear combination, right? Because it's 3. So for this one, which is the easiest method? Finding what? Maisha, do you know? No. Shivu? Determinant. So even if you try to find the inverse, first you have to find the determinant. And when you find the determinant, if it's not 0, that means they are independent, they're good. But if it's 0, that means they are not good, they're bad. So let's find the determinant. 1, 0, 0, 0, 1, 1, 1, 0, 1. My favorite method of finding 3 by 3 determinant is rewrite the first two columns. So 1, 0, 0, 0, 1, 1. So the first right diagonal gives us 1 plus second right diagonal is 0 plus third right diagonal is 0. And we are subtracting first left diagonal is 0, second left diagonal is 0, third right diagonal is 0. So everything is 0 except the 1. So we found our determinant is not 0. What does that mean? Are they independent or not independent? They are independent. So yes, these are 3 linearly independent vectors. Since we have 3 independent vectors in R3 space, do they span entire R3 space? Yes. In order to span your space, you have to have n many independent vectors. So R2 needs 2 independent vectors. R3 needs 3 independent vectors. R4 needs 4 independent vectors. So number of independent vectors has to be same as the dimension of your space. Okay, clear? So in the exam, I'm going to give you something like this, a set, and I'm going to ask you, are they linearly independent? Do they span the entire space? And then later we're going to learn about bases. So we're going to have another concept. The next set has 4 vectors in which space?
R3.
R3. We're still in R3, but we have 4 vectors. So can 4 vectors be independent in R3 space? No. One of them is definitely linearly dependent. It doesn't matter which one is dependent. Then the second question comes. Well, we know one of them is out, so we left with 3 of them. Those 3, are they independent? So how many independent vectors you have? If you have 3, then they still span. If you don't have 3, then they do not span. So how many independent vectors we have in this set?
Well, at least 1.
At least 1, but that doesn't tell us do they span the entire space. In order to span R3, you need 3 independent vectors. So we need at least 1. So we need 2 more. How can we find out whether we have 3 independent vectors or not?
Each of them is 1 first, right?
So do you know which one to eliminate? Last one? Usually, yes, the last one is a combination. Usually, but not always. So if the last one is out, then how do you figure out whether the remaining 3 independent or not? It is the determinant. And surprisingly, we have the same 3 vectors as the left one. But there is a surprising thing here. Let's say we did not eliminate. So this one is yes, because we have 3 linearly independent vectors in R3. So yes, they are spanning set. So you have to just cross out 1 and then find the determinant of the other 3. But now if you did not cross out the third one, but you crossed out the first one, do you still get the determinant not 0? Let's see. 0, 1, 1, 1, 0, 1, 1, 2, 3. If you try to take these 3 and make a matrix, so we have 0, 1, 1, 1, 0, 1. So the first right diagonal is 0, second right diagonal is 2, third right diagonal is 1. Then you're subtracting. First left diagonal is 0, second left diagonal is 0, and third left diagonal is 3. What's the result? 0. You see the surprising thing? So you actually have to check not only one matrix, you have to check at least multiple metrics to see whether you have determinant 0 or not. This one gives you 0 because this vector you have is a linear combination of the other two or other three. Okay?
How, is there like a way to figure out which one for them?
Reduced echelon form. If you use reduced echelon form instead of determinant, then you're going to see whether you have infinite solution, no solution, or unique solution. If you have unique solution, then they're independent. If you don't have unique solution, then they're dependent somehow. Or if you don't want to do reduced echelon form, you have to just take out one vector and find the determinant 3 times. So we took out the first one, we got this one is no. Then you can take out the second one and then use these 3 and then do the same thing. Or you can take out the third one, do this, or you can take out the fourth one. So do it four times. Because you don't know. Like here, we are lucky because we have the same result as the first one, same 3 vectors. So we know the first 3 vectors are independent. But in the exam, how do you know? So you have to check. I mean, in the exam, I'm going to make your life easier because you don't have enough time. So I'm going to give you one vector that is clearly visible that is independent. So you can cross, not independent, so dependent. So you can cross that out and then take the determinant of the other 3. Here is not visible, right? 1, 2, 3. We just guessed it. 1, 2, 3 is independent. But in the exam, I'm going to give you something that you don't have to guess. You can see clearly. Okay. So with this, I have one more question. We're going to go over this question in our next class. So with this, we will be done with 3.2. So you have your homework. The last question will not be inside this homework set. So you can start doing your homework. It's section 3.2, question 1C, 2B, 3G, 4D, 11CE, and 12CDE. So the CDE is like they're asking which set of vectors is a spanning set for you, R3 or R2, whatever. Okay. So start doing them. I'm going to put the deadline a little bit later, not next week. And then we are going to start 3.3. 3.3 and 3.2, they are very close to one another. So I'm going to assign 3.2 and 3.3 homework together. And there's no homework for 3.1 because 3.1 was just basic information about subspace and questions. So have a good weekend, everyone. See you again next week, Monday, at the same time in the same classroom. Be safe.
You know, like that little diagonal trick, to find the determinant. You can only do that for 3x3.
3 by 3. It doesn't work for 4 by 4.
And it works, it's just not right.
It's not
I
right.
did it. Yeah, no, I was about to say, because I did it. On the
know.
homework, I did it with the 4 too, and I'm like, it
I
feels wrong.
I did it also first time. I thought probably it's for any type.
Yeah.
And then I realized, oh man, it's uniquely for 3
Yeah,
by
I
3.
know. That's why I was like, dang, like it would work perfectly for 4x4 as well.
For 4 by 4, you have choices. Use reduced echelon form to make it as a triangular matrix, or at least have 5 zeros anywhere.
Or
You can do inspections.
or what's the other thing you called? The long one? Where you
Cofactor expansion, yeah.
I low-key like cofactor more than like
You have to do it 4 times. Actually, for
Yeah.
3 by 4, 4 by 4, you have to do many more times.
yeah.
1 for 4, 1 for 3. So you have to do it many times. So I think 4 by 4, 4 by 4, row echelon form is better. At least have a triangular matrix or 5 zeros. If you have 5 zeros, then do inspection with the cofactor. Okay.
Thank you, Miss. Have a good weekend.
Maisha, question?